So good morning, afternoon, evening, or good night, depending on when you're getting these notes. If you notice next to somewhere around where you got this video, there are also some notes that you can go ahead and print. This is for my first attempt at this, so let's see how things will go. So this is section 5.2, solving quadratic equations by factoring, the second day of this. Yesterday what we went ahead and did is we factored using basic factoring. With a it was 1, or California method when a was greater than 1, different than 1. Today we're going to look at special patterns. Can I find a special pattern and factor out something without having to use California method or basic factoring? So the first one that we're going to use is called the difference of two squares. Notice the first thing that I have to see, I have to recognize, I have to notice, is that my first two terms, A and B, are both perfect squares. It's A squared minus B squared. And that's going to give me my product of A plus B times A minus B. This is a difference of two squares. This is a binomial because I have two terms, A squared and B squared. And it's a product of two binomials because I have two terms, A plus B, A minus B. So let's look at our first example and see how this works. X squared. Well, is x squared a perfect square? Yes. This is the letter x squared, the variable x squared. The second one, number 9. Is the 9 a perfect square? Yes. What? This is 3 squared. Notice this is a difference of two squares. We're not able to factor the sum of two squares right now, but we can factor the difference of two squares. So this tells me that my answer is going to be x plus 3, x minus 3. And that would be my final answer. But you're sitting there going, but wait, how do I know that's true? Well, let's test this by foiling. FOIL. First, x times x is x squared. Outer, x times 3, negative 3, is negative 3x. Inner, 3 times x is positive 3x. And last, 3 times negative 3 is negative 9. Notice that when I do this, my two middle terms, negative 3x, positive 3x, cancel out, leaving x squared minus 9. This is a difference of two squares, so notice my answer is x plus 3 times x minus 3. Let's go ahead and try a different example. So notice I have factor 4x squared minus 25. Notice that this is a difference. So it could possibly be a difference of two squares. So is 4x squared a perfect square? Yes. What? 2x squared. Is 25 a perfect square? Yes. What? 5 squared. So it's 2x squared minus 5 squared. So that tells me that my answer is 2x plus 5 times 2x minus 5. And that's my answer. Again, if I'm unsure, I can go ahead and FOIL. First, 2x times 2x is 4x squared. Outer, 2x times negative 5 is negative 10x. Inner, 5 times 2x is positive 10x. And last, 5 times negative 5 is negative 25. Again, notice my middle terms, negative 10x, positive 10x cancels, leaving me with 4x squared minus 25. So my problem is checked. I have my answer, 2x plus 5 times 2x minus 5. That is a difference of two squares. Is that the only special pattern out there? Can I recognize other patterns? Yes. Our second special pattern goes like this. It's called a perfect square trinomial. A perfect square trinomial. Go ahead, if you didn't print off the notes, you can go ahead and write this down. Notice it's a squared plus 2 times a times b plus b squared. This is what I would be looking at if I was given a problem and I want to factor. Notice I have a perfect square in front. I have a perfect square at the end. In the middle is 2 times the first term times the second term. If it matches this pattern, my answer can then be a plus b times a plus b, or a plus b quantity squared, which is what we really want as our final answer, a plus b quantity squared. Let's look at an example like this. Notice my first term, x squared. Is this a perfect square? Yes. What? It is x squared. Look at my last term, 36. Is this a perfect square? Yes. What? 6. So let's see if it fits the pattern. Is 2, and notice the 2 is in my pattern, times x times 6, is that 12x, my middle term? It is. Since it fits the pattern, I can say that this is a perfect square trinomial, and I can say my answer is the first term plus the second term times the same thing, the first term plus the second term, which is the same as x plus 6 quantity squared. There's my answer. If I was to FOIL this out and check this out, we'll do this in green. First, x times x is x squared. Outer, x times 6 is positive 6x. Inner, 6 times x is positive 6x. 6 times 6, last, is positive 36. So if I combine like terms, x squared plus 12x plus 36. Notice that is the exact same as my original problem. So therefore, yes, this is my correct answer. Whenever you FOIL, you should come up with the same answer, because that is my check. So let's go ahead and try the second one. Notice the difference here. There's not much difference, excuse me, too far, between these two problems. The only difference is I have a minus instead of a plus. And notice that translates to subtraction in all three of these over here. So it's a minus b, a times a minus b, which is a minus b quantity squared. That's what my answer is going to look like when it's a subtraction in front of that 2ab, in front of that middle term. Let's try an example like this. So, again, I want to look at this and ask, is x squared a perfect square? Yes. What? X squared. Is 16 a perfect square? Yes. What? 4. So, again, to follow my pattern, is 2 times x times 4 8x? It is. Notice it is negative 8x, but that will go ahead and come out in my pattern. 2 times x times 4 is 8x, so that tells me my answer is x minus 4, x minus 4, yes, again, multiplied, and that's equal to x minus 4 quantity squared, and that's my answer. If I FOIL this out, I'm going to, again, in red, x times x is x squared, first, outer, x times negative 4 is negative 4x, inner, negative 4 times x is negative 4x, last, negative 4 times negative 4 is positive 16. Again, my middle terms combine, so I get x squared minus 8x plus 16. It matches my original problem, so I have done it correctly. Let's go ahead and do a couple more examples. So, factor 9y squared plus 24y plus 16. Again, I want to start this by asking the question, is 9y squared a perfect square? Yes. What? 3y squared. Is 16 a perfect square? Yes, what? 4 squared. Again, to follow the pattern, is 2 times 3y times 16? Well, 2 times 3y is 6y times 4. Well, that was totally wrong. Is 2 times 3y times 4 24y? 2 times 3y times 4 is 24y, because 2 times 3y is 6y, times 4 is 24y. It fits my pattern, so I can say that my product is 3y plus 4 times 3y plus 4, which equals 3y plus 4 quantity squared. But here's my question. What if you forget to ask if they're perfect squares? What if you're not sure if they're perfect squares? Can I factor this any other way? The answer is yes. I can use California method. In California method, if you remember, I can go ahead and say A times C and B. What multiplies to be A times C and adds to be B? Well, 9 times 16 is 144. My middle term B is 24. So what multiplies to be 144 and 24? I'm not going to list all the factors this time, because I know that 12 times 12 is 144, and 12 plus 12 is 24. So just like what we've done before, I've done my factoring. Let's go ahead and do my fractions. So my fractions would be 9y over 12, 9y over 12. If I reduce 9y over 12, I get 3y over 4, and of course I get that twice. I can go ahead and now make this, after I've simplified, into my factors. So this is 3y plus 4, 3y plus 4. And of course, that is 3y plus 4 quantity squared. Either way, I end up with the exact same answer. I think, noticing the special pattern, the perfect square trinomial, is an easier way of doing it, but you could always do it by California method if you don't notice that. Let's try another one. 49r squared minus 14r plus 1. Again, if I'm trying to see if this is a perfect square trinomial, is 49r squared a perfect square? Yes. What? 7r. Is 1 a perfect square? Yes. What? 1. Check the pattern. Is 2 times 7r times 1 14r? Yes, it is. So that means, notice it is subtraction. So this is my perfect square trinomial difference. So that means my answer is going to be 7r minus 1, 7r minus 1, again multiplied, and that's equal to 7r minus 1 quantity squared. That's my final answer. Again, if I did not notice that this was a perfect square trinomial, I could always do this using California method. A times C, 49 times 1 is 49. B is negative 14. What multiplies to be 49 and adds to be negative 14, again, you can list all the factors. It's 1 and 49, and negative 7 and negative 7. Negative 7 times negative 7 is positive 49, and it adds to be negative 14. So those are my two factors. California method, I want to go to my fractions next. So I do 49r over negative 7, 49r over negative 7. I reduce the first one, I get 7r over negative 1. Reduce the second one, I again get 7r over negative 1. Make these into my factors. This is 7r minus 1 times 7r minus 1, which of course is 7r minus 1 quantity squared. Again, the same answer I got up here because I'm solving the same problem just in a different way. I can do it either by perfect square trinomial or by California method. I think the perfect square trinomial is easier if you can recognize that they're perfect squares and it fits the pattern. So we have one more factoring topic that we want to go ahead and use and try. So let's go on to these examples. Factor out a common term first. Notice the word first. From now on, you want to do this first. You always ask, is there a common term I can factor out? If I don't factor out my common term, it's likely I'm not going to have, it's likely it's going to be more difficult to factor out my problem, my polynomial. So I want to factor out my common term first. So 5x squared and 20. What's my common term? 5. So I factor out a 5. Out of 5x squared, I'm left with x squared. I factor out a 5 out of 20, I'm left with 4. So I factored out my common term. I'm left with a binomial, 2 terms. Ask yourself the question, is x squared a perfect square? Yes. What? X. Is 4 a perfect square? Yes. What? 2. So notice this is a difference of 2 squared. X squared minus 2 squared. So I can then say that this is x plus 2, x minus 2, and that's my final answer. Again, I can always FOIL the check, but that's my answer. And I notice that this is a difference of 2 squares. Let's try our next example. Factor, I'll slow down. Let's try our next example. Factor 6p squared plus 15p plus 9. Again, I need to ask, is there a common term I can factor out of 6p squared, 15p, and 9? The answer is yes. The common factor is 3. If I factor a 3 out of 6p squared, I have 2p squared. If I factor a 3 out of 15p, I'm left with 5p. If I factor a 3 out of 9, I'm left with 3. So now let's see if this is a perfect square trinomial. Trinomial because it has 3 terms. Is 2p squared a perfect square? No, it's not. So it cannot be a perfect square trinomial. So what do I do at this point? The only thing I have left is California method. A times c, what multiplies to be a times c, and adds to be b. A times c is 2 times 3, or 6. B is 5. What multiplies to be 6 and adds to be 5? Well, I can have 1 and 6, or I can have 2 and 3. If I'm subtracting, 6 minus 1 is 5. But notice I have a positive on both of these, so I'm not subtracting. So 2 plus 3 is 5, and this is what I'm going to have to use because I'll need to add both of these because there are no negatives in my original problem. So at this point, I have 2 and 3. Let's go ahead and set up my fractions. So that's 2p over 2 and 2p over 3. The first one reduces to p over 1, leaving it as a fraction. The second one doesn't reduce at all. It's 2p over 3. Let's go ahead and make this into my factors. I get p plus 1 times 2p plus 3. And you have to be very careful because I have this 3 sitting over here that I factored out. That has to be part of my answer as well because it's one of my factors, and there is my answer. Let's go ahead and do our last three examples. So first we want to factor 2u squared plus 8u. Again, is there a common factor in 2u squared and 8u? I have a common factor of 2, but I also have a common factor of u. If I factor 2u out of 2u squared, I'm left with 1u. If I factor 2u out of 8u, I'm going to be left with 4. So I get 2u times u plus 4. Is this a perfect square? A difference of two squares. Well, first of all, it's not a difference. Secondly, u is not squared. So this is my final answer because there's no other way to factor this. 2u times u plus 4. Letter G. Let's see what this does. 4x squared plus 4x minus 4. Again, is there a common factor? The answer is yes, 4. If I factor out of 4, I get x squared plus x minus 1. If I look at this problem, it looks like this could possibly be basic factoring. Basic factoring says what multiplies to be c and adds to be b. What multiplies to be -1 and adds to be +1? Nothing. There's nothing that will multiply to be -1 and add to be +1. So my final answer is 4 times the quantity of x squared plus x minus 1. That's it, because x squared plus x minus 1 is not factorable. And our last example. That's not our last example. Let's try our last example. Get rid of that dot. Okay. Negative x squared minus 6x minus 8. Whenever I have a negative in front of my x squared, it's really nice to go ahead and factor out a -1. So I have x squared plus 6x plus 8. Again, I can go ahead and use basic factoring. What multiplies to be c and adds to be b? What multiplies to be 8 and adds to be 6? Again, I can list all my factors if I want, but hopefully you can figure out that 2 times 4 is 8. 2 plus 4 is 6. So my two factors are 2 and 4. Keep my negative in front. So this is x plus 2, x plus 4. Those are my factors. Nothing else is factorable. I do have the negative in front. There's my answer. And with that, we're done with our first. We're going to go a little over 23 minutes. That's still the wrong page. Here is your homework, page 261, numbers 47 through 64. All problems can be factored. Good luck, and I'll see you tomorrow.